Good morning, good afternoon, and good evening, everyone. Thank you for joining us today and welcome to the DAS RCN webinar on instrumentation. I am Casey Adderhold from Incorporated Research Institutions for Seismology. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box, not the chat box, on your Zoom control panel. At the end, we will read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. Automatic captions are available to be turned on and off on your Zoom control panel. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a series of webinars on different topics within distributed acoustic sensing. I'm going to pass this to Dr. Yingping Li now to get us started.
Thanks, Casey, for organizing this. Thank you all for joining us today. My name is Yingping Li, and I am a co-leader of the Instrumentation Working Group of the NSF-funded DAS Research Coordinator Network. Today, we will hear from some of our vendors participating in this group as part of a series of webinar showcases by the DAS vendors and the DAS service providers. This will establish a platform to bridge users and the vendors, leading better communications among the DAS societies. We welcome others to get in touch if they would like to present at one of these in the futures. Our first speaker today is Andreas Chavarria from OptaSense. His title is High Resolution and Long-Range Measurements with OptaSense QuantX and ODHx Interrogators. Dr. Andreas Chavarria is OptaSense OFC Technical Directors. He oversees a team of experts of fiber-optic sensing. He has 20+ years experience on the earth science and engineering monitorings. He was the geophysical processing manager at SR 2020 and Paulson. He has extensive publication reporting covering topics from seismology to exploration, seismic, and engineering. He holds engineering geophysics degrees from UNAM and a PhD degree on geophysics from Duke Universities. I will hand over to the Andreas. Thank you.
There you go. Sorry. Perfect. So Casey, can you just confirm that I am showing my screen?
Yes.
Perfect. Excellent. Well, thank you all for attending. I'm going to give again a few updates on some things that we have been working on fiber optic, and again, certainly I tailored it towards seismic measurements and things that we're doing with seismologic surveillance. So just a little bit of an intro. OptaSense was founded in 2007. We are part of the Luna Innovations company, so we are 130+ employees distributed in the US, UK, Canada, offices in the UK. OptaSense, again, we have been deploying this technology for many years for anything from linear assets, pipelines, perimeters, borders, transport, energy, a lot of downhole surveillance. So we're very proud that we're really, many of our systems are sampling really tens of thousands of kilometers. We're sampling hundreds of wells worldwide. We have hundreds of publications in major journals. So again, we do have a extensive publication record. So if anything I'll be showing today has been published, so I can share the links. So OptaSense manufactures the IUs, which is what I'm going to be focusing today in this presentation, but we also work on very special cables to do certain specific sensing, so things like strain, temperature, things like that. We also provide software. We have software for analysis, the XX software. But also, again, as it was mentioned, we do know that this fiber optic business, it's essentially a real-time monitoring thing. So we have a lot of software solution to basically optimize the measurements in real time, do processing in real time. So again, I'll be showing the data, but again, in this talk, I'll be focusing more on the interrogator side of things. So where does this all start? So again, we have been monitoring, again, pipelines, perimeters for a very long time. So here I'm just showing an example of a pipeline in Mexico recording a couple of large earthquakes in Mexico. Again, this was intensity based. And again, this was done for a long time. And then around 2007, someone asked us, well, can you connect that thing in a downhole and connect, instead of intensity measurements, collect quantitative data with full amplitude and phase coherent data. So we connected it and we basically got our first seismic measurement on a fiber optic. And we were like, well, you know, that looks very exciting because you don't need to put any geophones in the ground. So short iterations, again, we started to increase the signal to noise, the fidelity of the systems. Our third generation system, actually, I'll be showing a lot of this data from this specific IU. And you can see basically that progressively the signal to noise and the quality of the signals has improved. I'll focus a lot of the time on the aspects of our fourth generation, which is what we're deploying for the most part this day and age. So again, it has very low noise floor, high, very nice waveform data. We are using these for fully instrumented seismic networks. So again, here I have set with 3 different fibers in different configurations, recording an event. So again, nice clear PNS. And on the last iteration, again, this is our newer unit, our 5th generation. This is our long range. So of course, increasingly we're facing fibers that are longer and longer. So I'll be showing some data from this specific tool. So again, certainly this technology was started for the oil and gas industry, and now has been really adopted by academia, by different seismologic networks, and that is very exciting. Because again, it really is opening the door to taking advantage of fibers that are available to us. All of this is dark fiber, and really I need to start by thanking Biondo at Stanford and his team for really starting a lot of this work by connecting the fiber in the Stanford loop. So again, there's many fibers that show that we could use dark fiber to detect earthquakes, to do different types of seismological analysis. So him and his team come to mind, Eileen, Ariel, Nate, this is a paper from Nate specifically, have shown that we can use these fibers. This is our 3rd generation IU, our ODH3. And again, we can record very nice quality earthquake. This teleseismic events, a 5.8 recorded from Oklahoma, recorded in the Stanford array. And something that I'm going to be focusing on in this presentation is, well, why are these IUs unique? What makes them special that allows us to do these measurements? And I want you to pay attention to the bandwidth. So in this case, I have very low frequency. So I'm going to be focusing on the noise floor and the bandwidth of this unit. This is a couple tenth of a hertz to 1 hertz. So again, we are very rich on that spectrum. So again, we have 2 IUs that I'm going to be talking about, the ODH4, our QuantX. They basically allow for variable gauge length acquisition. Basically, depending on the signals that you want, you can set the gauge length. Again, whether it is shorter fibers, less than 12 kilometers, or longer fibers, all the way from 15 to 100 kilometers, we can run them. What is unique is that they are DC coupled. They're incredibly sensitive. We're in the nanostrain, in the millikelvin sensitivity. I'll talk about that shortly. They are basically can connect to any fiber that exists, enhanced fiber, single mode, multi-mode, fiber brag, all types of cables. So again, there's very versatile, but for the purposes of this presentation, I'll focus on the cheapest dark fiber single mode because that's what we have available. So again, all the enhancement is done at the IU. And again, we can connect to all types of optical infrastructure. So something that is very exciting about these tools is that, again, you have full functionality as far as how you operate them, changing ping rate, changing the gauge length, launch power, On the case of the ODH4, we can stack signal from different lasers, change channel spacing and things like that. So again, all of that flexibility is very important because sometimes, let's say, if you may be wanting to do teleseismic that requires a longer gauge length, or you may be wanting to do near surface geophysics that requires shorter gauge length. So this is an example basically of different seismic records acquired with the same IU, but at different gauge lengths. So again, you can see that, of course, your signal to noise will change depending on how you run these things. But again, really at the end of the day, you want to basically make sure that for your signals of interest, given their velocity, given their frequency, you can optimize the optical settings. So again, these IUs provide you that functionality. And this gauge length story is important. Again, certainly from a seismic point, I would say for earthquakes where you want to run larger things, it's good to have the option to have longer that we have here. But this is an example. It's actually something I'm showing this because it's just in review. And this is a comparison of a geophone and a DAS set of cables. This is work done by Ellmauthaler et al. And Peter Hobart at Berkeley. And basically, they have been validating that these DAS systems are comparable to other point sensors that we have been using for many years. And basically, in this case, they're using it near surface geophysics. This is for surface wave dispersion analysis. And what they have been able to show is that those dispersion maps from the geophones basically can be matched by the high resolution. So this is ODH4 data. It shows that basically at 2 meter gauge length, again, we can replicate that response. Here for comparison, we have another type of IU. This is a 10 meter gauge length IU, and you can see that certainly if you run this with a longer gauge length, again, you start to miss that type of information. So very critical to have the ability to record the data for the signals that you need. So here, basically, we have seen that short gauge length data with this high resolution IU basically can really replicate the dispersive modes for this specific study recorded on a surface fiber. So that's very exciting because, again, it tells us that sensitivity-wise, again, we are basically at the point where we can actually match comparable with like existing sensors, but in a much simpler way. Because again, fiber, it's easier to deploy. You don't have mechanics and things like that. This is another paper from Peter Hobart, where it just got accepted. So again, you can download this already. But again, as part of this same study, again, they basically they process, in this case, they process the geophone data to match the DAS. They did the conversion in that direction. Sometimes it's done in the opposite direction. And here, what is exciting is, again, they were running different types of cables, different types of sources. Here on the right side, I have a hammer source. On the left side, I have a portion of a sweep. And this is a comparison between geophone and two different cables with fiber-optic DAS. And you can see that basically, for the most part, we're tracking certainly the amplitudes. The instruments are in depth. I encourage you to zoom in into this area later on. And it really, I can tell you, it's really a crazy match. I was very surprised when I see this. I was very proud that we could have that type of resolution. So again, this tells us that we really can use these IUs to record this type of data. But going to the sensitivity side, again, when we say, well, 1 nanostrain, what the hell does that mean? So I think to put it more in things closer to what the attendees in this forum usually are, which tends to be seismologists or geophysicists, let's compare it against a seismic network. So this is work from the team from Xiongwen Shan at Caltech. They've been doing a lot of work with these tools. It's an example where we have the San Andreas fault. We have a 10-kilometer fiber connected to our 3rd generation system. And they recorded an aftershock sequence for a number of months. So here I have the distribution of events with respect to time. We have very nice quality waveform data. What's very exciting is that when we look at the magnitude plot with respect to time, we can see that all of the events on blue are the events located by the Southern California seismic network. Again, this is a part that is very heavily instrumented, so it's a nice network to begin with. But we can see that the DAS fiber actually is adding a lot of other events with almost 1 magnitude lower, which again is super exciting because again it tells us that these array sensors indeed have that type of sensitivity. So again, we can complete the catalog in magnitude range. So again, this is something very exciting. And certainly, again, this is array processing. So this is another paper. This one is from Adderholt and Aldous, just got published a couple of months ago, where again they took that same data, and what they did was they did different types of processing. In this case, they ran it through a curvelet denoising. Basically, the signals from the DAS, again, these are fiber that's in the environment. So there's some vehicles. I'll talk about this at the very end of this talk. But they were able to show that when they look at the variability of events with respect to time, of course, when there's more traffic, you have more noise, you detect less events. So you can see the Southern California network does pick some events, but DAS picks significantly more. And certainly the effect of denoising cleans and detects even more events, but even the data without so much processing does get you more event count than the conventional seismic vector. That again, I think it is very exciting. Yeah, so this is of course a traditional earthquake setting, perhaps a little bit different one. This is from a volcanic setting. So this is a glacier that we have been monitoring up in British Columbia. This is work by Klassen et al. And again, recently published. And again, we have been detecting a lot of events, also with this third generation system. Again, multiple events recorded compared against conventional broadband seismometers, against conventional geophones. So here what I show here is the distribution of events that have been detected by the three systems. And you can see that the DAS does pick significantly more events than the other tools. So again, it's very nice. Once you look at the power frequency distribution of the number of events, you can see that again, our catalog is significantly more complete compared to the other more conventional tools. And again, it's easier to deploy. So again, this tells us that the sensitivity of DAS systems, and even with this third generation system, is basically at a point where we can do this type of analysis. So something that is very unique about our systems at OptaSense is that we are a fully DC coupled DAS. What this means is that we have here with respect to frequency, we have a flat noise floor pretty much extending to DC. So this is very exciting because there's other DAS systems that basically are going to have some sort of taper. And this has big implications for seismic because, yeah, it may look, when you have these tapers, it may look like you have higher frequency, but it means that you're losing amplitude information at the low frequency, which is very important for teleseismic, for some sort of surface wave inversions, impedance inversions that require that low frequency data. And certainly at those low frequency components, again, we start to do other physics like strain, deformation, temperature. So again, something very important about this specific IUs, and these two IUs that I'm talking about, is that we have a flat spectrum. So, so what else again can we do out of this broad bandwidth? So certainly I showed you that we can detect a lot of events. So here, going back to that glacier example, so here I have an example where all of a sudden we are detecting volcanic tremors. So again, this is the low amplitude events, but again, you can clearly see them in one of the in all of the DAS channels. Again, what is very exciting here is that on the spectrum, again, when you look at the frequency distribution with respect to time in this spectrogram, you can see that again we're getting a very, very rich spectra at super low frequencies, which again, it's something that a DC coupled DAS will provide. So this is from a monitoring point of view. Of course, we always have the imaging point of view. This is something that just got published in Nature last week or maybe this week. But essentially a fiber, again, this is a marine cable where essentially we're looking at Schulte waves recorded to do high resolution imaging of the near surface. So again, this is in the Irish Sea. And here I have an example of the shot record or seismic record. Again, they run different types of sources. Oftentimes people will use interferometric gathers from permanent noise recordings. What's exciting, again, and again, something to keep in mind about this IUs is that you have a flat spectrum. So again, you really can have some of those frequency modes being recorded at very, very low frequencies. So again, you're doing inversions, cycle skipping problems, things like that are challenges that are going to be healed by using these type of interrogators. In this case, they looked at the Schulte wave analysis to do that imaging of the near surface. In this case, this is going to be actually for a wind farm. So they wanted to make sure that they had a high resolution shear wave structure to see where the instrumented wind farm will be located. So again, this is a combination again of this very high resolution sensing. Again, this is a 4-meter gauge length data, but again recorded with this broad bandwidth data sets. So closer to home, and again, this is of course I pay a close attention to this because here we have the San Andreas fault. Here we have our fiber array, and my house would be somewhere on this side over here. So I take this very seriously. So certainly for ground motion analysis, it's very important to basically characterize the Earth. So again, in this case, this also worked from the Caltech team, where again, they have been able to show that, again, those surface wave analysis from our DAS data can get you very accurate pictures of the near surface. And basically here they're plotting DS30 against the site amplification. So you can see that you can see clear trends when you have these parameters, again, all derived from the continuous monitoring on the fiber optic data. So of course, this is the range. Again, I told you that our ODH4 unit is optimized for fibers that are less than 20 kilometers. Our QuantX system basically can record data to 100 kilometers. Again, that's the longest fiber right now we have connected to. And again, this is a 2.7. This is a fiber that is located in Long Valley. So this is an event 2.7, somewhere around Mono Lake. So we are quite away from the fiber, so almost 90 kilometers away from the fibers. But you can see very clear P and S arrivals along the entire extent of the fiber. If I zoom in here towards the very end, you can see the last 4 kilometers. Again, we have very coherent wave data. So again, it's very exciting. We're very proud that people are using this system to record longer and longer fibers. And maybe changing gears a little bit, just to tell you a little bit about what is unique about these IUs. I already mentioned that these things are flat spectra, or DC coupled systems. But again, this opens the door to other types of physics. So certainly on the seismic, again, we are maybe on narrow-minded, let's say from 1 hertz to maybe 100 hertz if you're using maybe more active seismic imaging. We do know that we can record a higher frequency data with this. But in the low frequency end, again, these systems are incredibly sensitive to temperature and strain. So I mentioned that sensitivity of nanostrain or a millikelvin. And that really allows you to do other types of physics with the same IU. Again, all of the parameters, all of the controls that are being run optically, you have full control of those things with this tool. So this is data from QuantX. This is very recently, was shown in this forum a couple of weeks ago by Ethan Williams, and he shared these displays with me. This is a fiber connected over in the Puget Sound. It's a 60-kilometer cable. And again, they've been recording all types of stuff, which again, is very exciting. And of course, we have here an example towards the very end of the 60-kilometer fiber, or the T phase for a given earthquake. So again, we know we can record those. But for my first time seeing a fin whale vocalization, again, that we were able to detect. So again, a lot of work being done by different groups. William Wilcock is involved in this project. Also recording ocean surface gravity waves in this specific cable. So again, you have a system that gives you the long range, again, broad bandwidth, so it allows you to do different types of physics. Another marine cable, this one is the Muroto cable offshore Japan. This is a 50-kilometer fiber. We recorded both earthquakes. In this case, I have an active shot record from a seismic, from an ergon array. And again, basically we have signals along the entire 50 kilometers. This data has been used for imaging, let's say near surface geophysics. I'm focusing here just in the very end of it, a very coherent data for the entire data set, and of course, broad bandwidth. So again, in this case, you have basically that very richness on the spectra at a couple of hertz, which again is very unique for this type of ocean bottom sensing. But of course, these tools, again, you are monitoring seismic, but when you process the data for other things, again, you can focus in the low frequency. Where we are going to be more dominated by things like temperature, pressure, They actually were able to show this work by Satoshi Ide, where essentially they showed that that same data could track different currents along the cable. So here I have a profile of the ocean floor where the fiber is located. So again, where we have this mountain in the ocean floor, again, we have larger eddies. In this case, the DAS data has been processed at low frequency, so we can track that type of tight and complex current processes associated to that, all of that water mixing. So because again, keep in mind that these tools, again, they have very, very high sensitivity to tiny temperature changes. On the mechanical side of things, this is an example from another fiber. This is located in the UK, where we have been doing with the British Geological Survey, where we have basically the problem of landslides. So in this case, we're using those fibers to, again, use interferometric shot records to do, again, our near surface analysis, again, of our velocity variations with respect to time. But again, this is, at the end of the day, this is a strain sensor that when you run it and process it for strain, we basically have the solution that, again, can track at different points along that fiber. We can make these maps of areas where the strain, maybe the fibers are being strained or are being constrained, are stretched or compressed in certain ways. So again, we can track, again, those changes in the strain in the fiber. So again, this basically allows you to start to look at the closest DC shift. Again, for those of you in the elastodynamics world, seismic, again, we focus on the seismic radiation, but again, these tools allow you to look at the pure strain response. So again, multiple applications from the same IUs, basically configure them to the signals that you want. And just to go back to that example from Caltech early on, from the San Andreas fault at Ridgecrest, I mentioned that, again, these tools, again, were recording. They show that they could suppress the noise from the cars using corblet transforms. But we can take, if we think of those cars as the signals, again, we can start to do other stuff. So again, this is also work by Wang et al. Also from the Caltech team with Xiongwen Shan. And this was published last year also in Nature. Fiber located around Pasadena. And again, they were recording during and before the pandemic. So they looked at traffic patterns using these fiber optic sensors. So again, we're capturing high frequency radiation as well. So they were able to see that, well, during the pandemic, actually there was not as much traffic. So people were actually driving at the proper speed compared to when it's fully jammed and you barely can move. So it was very interesting paper that, again, it shows that, again, these fibers are really very versatile and you can use them for many applications. So just in conclusion, again, these are DC coupled systems, all Rayleigh based. They are very sensitive to seismic. Again, we're detecting more events than conventional seismic networks. Both the ODH4 and the QuantX for long distance allow you full control of the optical parameters. And really, this is an important message because you should optimize the IU to measure the signals that you need, not what the IU can do. So if you want teleseismic, set it up for teleseismic. If you want near surface, set it up for near surface. So again, having that flexibility is important. Certainly, that flat spectra does give you other physics. Again, it can provide you long period data that beyond seismic can start to get you to strain, to temperature, other types of acoustics. So hopefully, if you have any questions, please let me know. There's my email, our web address. So again, all of this has been published. There's, as I mentioned, there's many papers out there. So please send me an email if you have any questions. Okay,
thank you. So we have some question here. Thank you, Andrea. So the first question is, Andrea, you said the fiber detected more events than the geophones. Are you saying fiber is more sensitive than the geophone?
Yeah, and I think that's right now, that's the direction it seems to be heading. Certainly when we first developed these tools, that was kind of like the goal, well, to have a system that is just as sensitive as the geophones. I think it's a combination also of the processing. I think the distributed nature of the array is basically enabling us to basically maybe filter and clean the signals to a point that, again, we are surpassing the detectability. But again, this example from the San Andreas, from the glacier up in Canada, some other stuff that we have been doing for industry does show that, again, once you combine the arrays, you start to detect more events.
Second question is, Andrew, what do you mean by the DC coupled system?
Yeah, excellent question. So basically it means that for those of you who are familiar with maybe an example, short period seismometer, you're going to have a flat ramp towards the end in the lower end. Borehole seismometers are going to have the same problem. They're going to have that flat ramp. DC coupled means that we are basically have a flat spectra or flat instrument response pretty much close to DC. So basically you are fully sampled at those super low frequencies. So when we do our strain measurements, we even have ways to compensate our signals with other tools to get you a true flat spectra down to close to 0 hertz.
Okay, we have another 2 questions. From that equipment, can you infer the pore size or shape of the matrix?
Well, I can talk here. This is more exploration seismology. So I can say that there is with active seismic data, there's been some work done on inversion of seismic images done with DAS, with high resolution borehole seismic DAS, and there's some interpretations on the petrophysical aspects of the rocks. As far as pore size, we're still using these are longer gauge length. Let's say the shortest, at least the data that I showed today, that's the 2 meter gauge length. So again, that's still larger than pore size. So you would have to interpret it more as a overall on that stratigraphic sequence. But there are also as part of the Loon organization, again, we do have a higher resolution. I use like more on the millimeter style resolution. So again, I can follow up with that one. We do have tools for that level of resolution.
Do you have any applications in the time variation detections?
I'm not sure I understand the.
Do you have any applications in the time variation detections? Probably he means 4D. Time variation detection.
Do you have any in time variation detection? Well, yeah, I can say I'm not sure what he means exactly, but yeah, certainly all of this technology has been deployed again for active seismic acquisition. So again, this is something that we use with active sources. Let's say right now a topic that is hot, which is carbon capture storage. We essentially can use seismic data from these permanent fibers, make images of the subsurface, come back after injecting the CO2 and see where the CO2 is migrating. So again, we can do that time-lapse processing with these types of tools. And again, this is the advantage of it over other tools is that these are true permanent sensors. Once you have the fiber in there, they'll take the heat, they'll take the pressure, very robust. So you also you have a 100-kilometer type of array from which you can do your seismic imaging.
Yeah, are the geophones response being compared near the resonance of the geophones?
Yes, and I think at this I'm actually I'm very glad that the team at Berkeley has been doing so much work with comparison with geophones for infrastructure monitoring. So I do encourage you to look at those papers, because again, it does show that with the proper setup of the fibers, with the proper cables, you actually can really replicate and really further to that enhance the length of what you can get with conventional geophone tools. So
yeah, how does the tools behaves recording data depending on the brittleness of the formations? How is the processing of the recorded events?
I'm not sure I followed that one. Question, Yingping, can you repeat?
Yeah, how does the tool behaves depending on the brittleness of the formations. How is the processing of the recorded events?
That's a good point. Yeah, and I can say that as far as the deployment itself, again, these cables again are very robust. Again, there's depending on the vintage of cable you have. Again, you can have everything from gold coated to things that will go in very high pressure and high temperature cables. Again, they're very robust. You really don't have issues of the cable breaking associated to the formation. Certainly from a petrophysics point of view, a lot of fracture monitoring is being done with these types of tools. So there's a lot of downhole fiber data that is used to monitor fracture networks. So again, there we're tracking basically the development of those fractures using microseismic data or using also the low frequency strain data from the DAS. So again, we can track basically how those rocks are fracturing as a result of different processes. So again,
okay, we have to cut short here because we have a second talk. So we have just like Andrew have the email, so we can continue this discussion later. We have two more questions here, but I think it's similar. So
thank you. I'll try to answer them online on the chat. Thanks for your attention.
And then we introduce our second speakers. Our second speaker is Andreas, the Ellmauthaler from Halliburton. His presentation title is Fiber-Optic Sensing of Subsea Wells, Challenges, Opportunities, and the Road Ahead. The Dr. Andre is the production manager of Halliburton Subsea Fiber-Optic Sensing product lines. With Halliburton, he has held various roles in the technology development, where he was responsible for the development of the novel fiber optic sensing solution for oil and gas applications. He received his BS degrees in the telecommunications engineering from University of the Applied Science, Salzburg, Australia in 2007, and his PhD degrees in electronic engineering from the Federal University of Rio de Janeiro, Brazil in 2014. Here I hand over to the Andreas. You mute?
Oh, there we go. Can you guys see my screen? Thanks for introduction, by the way, Yingping.
Yes.
Perfect. Okay. So with that, also, thank you very much for organizing this webinar series, and thank you very much for affording me with the opportunity to be here today to talk about Halliburton's DAS offering, and here particularly our offering within the Subsea space, which is a very exciting space to be in right now because there are a lot of hype around that space, a lot of opportunities, but also challenges. And I'm going to try to talk about those today, and then also give an overview of there we go. Sorry. So what I want to cover today is briefly the fundamentals of DAS, which I'm sure that you have already heard previously. But I want to talk about this because I think it's going to set me up very nicely to talk about the Subsea DAS challenge. Because there we do have to make changes to, I would say, our original paradigm on how we want to do things, just because of the increased fiber length and some of the optical attenuation challenges that we see there. This is then going to lead me to talk about our solution for Subsea, which we coined Odyssey. If time allows, I also want to quickly show you some field trial results that we can show at this point, where we're going to compare our Subsea solution with our traditional land solution and show how well they compare. And then I want to spend a couple of minutes as well, just on the road ahead, where things are headed in the Subsea world. And then I hope I'm going to be able to wrap all of this up now in approximately 15 minutes to give us 5 minutes of Q&A, where I can answer all of your questions. All right. So again, really briefly, just this is a sketch that shows how DAS works. On top, you can see that we have what we call a launch arm, and on the bottom, you can see a receive arm. There are many ways of doing this, so this is just one way a DAS interrogator can be built. But fundamentally, what is always the case is that they have a light source, which corresponds to a laser, that generates a continuous waveform, which then typically gets fed into a pulsar, which for all intents and purposes, you can think of like a shutter that we can control, and we just tell the shutter to open up for a very short period of time. And this will be generate a pulse that is then sent into our sensing fiber that in oil and gas applications is located downhole. As that pulse traverses the sensing fiber, a tiny fraction of that light gets back reflected. And we're talking here about something that happens at 100 dB below the power of light that we send in. So it's really very, very small. The best way to think about this is, I guess, when you drive through fog with your car and you have the headlights on and you have that glare coming back at you. That's pretty much what's happening here. And then we receive that light, and then we process that light, and then we want to get some acoustic measurement from that. So typically what we pick up is just changes in strain along that fiber. And then the sampling frequencies vary, but we have something that happens from 10 to 20 kilohertz. And as Andreas already mentioned in his presentation as well, strain can be caused by many effects. Acoustic is just one of them, but we also pick up something that happens in the lower frequencies that typically corresponds to temperature changes, for example, along the well, or changes in strain because of pressure hitting the fiber, for example. I have an audio sample here where we actually had somebody talk to the fiber, and this is just to give you an idea how it actually sounds, and it's going to show you how pristine the actual quality is that we get from the fiber. And I hope that's going to come through well for you guys. So let's give this a try.
Hello, this is Cole Madison from ExxonMobil at Halliburton's office, testing a voice recorder.
So what you could hear here is basically how the fiber just behaves almost classic microphone, which should also back up some of the things that Andreas showed before, just as how sensitive the fiber is. And then again, just think about all the opportunities that this opens up in terms of processing, in terms of applications. With that, again, I want to spend very little time on this one because I know that you know most of that already. There are many applications. Historically, where we started off was using that, at least in the oil and gas space, for hydraulic fracture monitoring. And you can see a very old picture here at the bottom, where we just wanted to see what is acoustically happening. And we were mostly interested just in acoustic power. So no waveforms at this point. We just want to see what makes the most noise. And based on that, we try to make decisions as to, for example, what frac zones take the most liquid? Do we have to change things around that? And that's where things started off. And this is already more than 10 years ago. The next thing that we tried to move into, and then Andreas spent quite some time and showed some excellent examples for that, was vertical seismic profiling, because we also felt that that's a low-hanging fruit in the sense that we know what a geophone is supposed to do. So let's see what the fiber does. And it also gave us a very good opportunity to convince many people in the space that what that's actually measuring is geophysically meaningful. And here to the right, you can just see an example that, I don't know how old it is, it may be already 5-6 years old, but we can see just how well that's actually able to measure the seismic field, which in this case is active seismic. And then we moved into other applications like leak detection. And then lately, we're trying to get into things that are a little bit more aspirational, which is production flow monitoring, where we actually try to characterize the flow rates, the flow compositions that are happening inside the well. And then we have some other ones as well, which is microseismic monitoring, baton monitoring. And there are many other applications that are not within the oil and gas realm, such as border security. The application that I want to spend the most time on here right now, because again, it sets me very nicely up for this push into the subsea world, is that a couple of years ago, we had this very, very good papers that for the first time actually looked into, can we use that for time-lapse monitoring, and here particular for offshore wells, where we have water gas injectors that simply try to push out the oil into producer wells. And what those papers have shown is that it's actually possible to use that. And then most importantly, it is possible to actually use that and complement, I would say, traditional ocean bottom node service, which are very, very expensive. And therefore, just by using that, we can just bring the cost down. And by doing so, increase the frequency of doing those services. And by doing so, obviously, operators will get a better understanding what the water gas frontier is doing. And based on that, just optimize their production strategies. So this is really where a lot of the excitement for them trying to get fiber into subsea wells comes from. Because now all of a sudden, you have this fantastic business model where you can see that, look, it may be challenging to get fiber into a subsea well, but look at all the fantastic things you can do once the fiber is there. So this is where things were a couple of years ago. And then we were confronted with, okay, how can we make that happen? And the reason why it wasn't that straightforward to actually do DAS in subsea wells is illustrated here. So in the tri-tree well, which is what we did before Subsea, the DAS interrogator was located really close here, which is next to the tree. And then we went through the tree, which was a pretty lossless operation. And then we sent the light pulse in here, and then we got light back from here, and then we analyzed it here. Like I said before, we get light back that is 100 dB-ish less than the amount of light that we sent in. And this allows us to get a robust measurement. Now in the subsea world, we have to take that interrogator and we have to move it all the way up to what typically is an FPSO or some type of platform. Because we don't want to marinize DAS interrogators because it's technically prohibitive. It gets very expensive and it's just not a good idea to begin with. When we do that though, out of a sudden we're confronted with having to traverse very long lengths of fiber just to get to the tree. So that's the first challenge. And I'm just showing one particular field here where you can see that if we accumulate that, we immediately get to something that is more than 10 kilometers, sometimes going to 20 kilometers. And there's some fields out there that have tieback distances that even extend longer than those 20 kilometers. So that's the first challenge. At first, we have to send that light all the way, those 20 kilometers to even get to the tree and get into the section of the fiber where we're actually interested in making a measurement. The next challenge is that typically in subsea fields, we also only have one FPSO that is then connected to a lot of wells. And those wells usually are at drill centers. In other words, this is just a manifold where you go into many wells. And every time you want to traverse one of those drill centers, you have to go through connectors. And since we're now at the seafloor, those are not going to be the typical connectors that we use in the lab, but those are actually going to be wet-made connectors. And those wet-made connectors are just by definition going to be lossier than the ones that we typically use in land/tri-tree operations. And there are many of them. So in this case, for example, every time we go through one of those drill centers, there are going to be 2 of those sticking out on each end. So we have like 2, 4, 6, 8 here. And again, each time we're going to take a loss, and each time less light is going to make it into the sensing fiber here, which subsequently is going to present a problem. So this is where things were. So quickly summarizing here, what I think I've already said. The first one was the reduced optical budget, again, caused by all of those additional attenuation points. And here also just as a, I guess an approximation, each time we have to go for one of those wet-made connectors, which you can see here, we take around a 0.5 dB hit. And also just to put this in perspective, whenever we lose 3 dB, it means that we lose half the light, pretty much. So this is the first one. And then the second one is just because of the increased fiber length. And it's not just that because of the increased fiber length, we're also going to lose more light. There's also an issue when it comes to the overall spectral resolution or frequency content of the data that we can acquire. Because the way that DAS works, as I showed before, is that we send in that light pulse, and then typically we have to wait for that light pulse to go all the way to the fiber end, backscatter light to come all the way up again before we can send in a new light pulse. If we would not wait until that first light pulse comes back, we would have 2 light pulses in the same fiber. We would get backscatter contributions from 2 points along the sensing fiber, and we wouldn't know from where the contribution came from. So we would basically have an invalid measurement. So because of that, we have to wait, as I said. And now the longer the fiber, the longer we have to wait. So for 10-kilometer long fibers, which is already a pretty long fiber in the tri-tree world, we, for example, can send 10,000 light pulses into the fiber per second. If we make that fiber longer, say 20 kilometers, this is going to drop to 5 kilohertz. And you can see the rule of thumb, the corresponding formula down here. So what that means at the end of the day, in subsea, where we have those step out lengths, out of a sudden, the sampling frequency, the amount of light pulses that we can send into the fiber drops dramatically. So for seismic, you could argue that maybe that's not the biggest of problems because, as Andreas mentioned as well, like what are we really interested in there? It's something that happens at the very low end, maybe at 1 hertz, and then it goes up to 100 hertz. And if you want to do microseismic, maybe we're more interested in the low kilohertz. But again, usually if you have like 5 kilohertz, we should be good. However, there are many other applications that rely on those high frequencies. Think about the way sand sounds, for example, where you really need those frequencies. And on top of that, a lot of the applications for that have been built on the assumption that we have at least 10 kilohertz, all of the applications that are coming from the tri-tree world. And it would just be a shame if we have to rewrite all of those applications just because now we don't get those high frequencies anymore. So this is again, I'm not going to spend too much time because I know I'm slowly but steadily running out of time here. But this is just one of the first experiments that we did a couple of years ago, where we just said, okay, look, what are we dealing with here in terms of optical attenuation and how this really impacts our measurements. So what we did here is that we took a fiber that was 24 kilometers long, we chopped it into pieces, and then after what I think is 18 kilometers, we just added an 8 dB attenuation point. That's really all we did. And then we hooked it up to a DAS interrogator from the time. And then what we did, we just looked at the optical energy, the optical backscattered energy coming back from that fiber. And two things that we can observe here. A is that for the first 18 kilometers, we obviously get a lot of light back, as you can see here. And what you can see as well is the characteristic one-way optical attenuation of single mode fiber, which comes in at around 0.2 dB. However, once we traverse that 8 dB attenuation point, what you can see is that the backscattered light coming back from the fiber pretty much flatlines at this point. So when we saw that, that was actually a quite scary moment, because that's when we realized, okay, I mean, it seems like that our traditional methods of doing things for subsea are not going to cut it anymore. And we need to do something else in order to be able to recover from that attenuation point and basically get as much light back as you've seen before, because only then we can actually make a robust measurement. So that was the first challenge. The next challenge, and this is again, I already talked about this, was the increased fiber length. So here on top, you can see the optical energy coming back for a 4.5 kilometer fiber. And compared to the previous slide, what I did is what we could see distance on the x-axis, I swapped that for time. So now what we can see is that for a 4.5 kilometer fiber, it takes around 45 microseconds for all the light, all the backscatter light to come back. We have some guard window here, and then after 50 microseconds, we can send in a new light pulse. And by doing so, for example, we get a DAS sampling frequency of 20 kilohertz, and we get a spectral bandwidth of 0 to 10 kilohertz. So this is the tri-tree case. And what we would see here is going to be good data quality. And again, that's what we would expect. That's what a lot of the algorithms that we built for DAS expect in terms of bandwidth. And then here at the bottom, you can see what happens if you have to traverse the same fiber as before, just without that attenuation point now. And you can see that we have to wait much longer, in this case, 230 microseconds before we can send in a light pulse. In this case, we had to wait until 250, and that's when we can get light back for the second light pulse. That then drops our sampling frequency to something which is only 4 kilohertz. And again, that just brings down the bandwidth to 2 kilohertz, which again, then we lose all of the good high frequency content that is needed. So also at the beginning, what we then tried to do is to quantify what all of this means in terms of how many dBs are we losing, how many dBs do we need to recover to have a viable solution for the subsea world in terms of DAS. So the first thing that we did is we looked at the downhole sensing fiber length. And fortunately, that was the only thing that did not change, in the sense that typically for land, we look at something that is less than 10 kilometers. Also in subsea, most wells are significantly less than 10 kilometers. Something that is completely new in subsea is the fact that out of a sudden, you have umbilical fiber, meaning the distance between the FPSO, the platform, and the tree. And that can be anywhere from 5 to even 100 kilometers. And then if you just use a case, for example, for one of Exxon's Guyana completions, where it's around 12 kilometers, we said, okay, great. If it is 12 kilometers, then we can assume that having to traverse that results in around 4.1 dB of SNR loss. Then the next thing is the pulse repetition rate, where we say, okay, great. Before we could use 10 kilohertz for a 10 kilometer fiber, and then depending on the length of the fiber, we go all the way out to 50 kilohertz. That is certainly not true in subsea anymore, where out of a sudden we get down to 1 kilohertz to 8 kilohertz. And that also hurts us in terms of SNR, because one of the drawbacks of DAS is that we actually cannot use anti-alias filters before we acquire the data. So whatever noise we pick up, it's going to be spread over our entire bandwidth. So the longer the bandwidth, the more it can spread, the lower the density of that noise is going to be. So the less amount of light pulses we can send, the higher that noise is going to go. And here, the rule of thumb is that every time the pulse repetition rate drops by 2, our overall noise floor is going to increase by 3 dB. So this is what we did here. So we just said, okay, probably for subsea, what is going to happen is that our pulse repetition rate is going to at least drop by 2, and we're going to end up with a loss of 3 dB. And then we also have those optical connections, where we're going to see, just because of having to go through all of those wet mate connectors, SNR losses that are going to be pretty high, and in this case, for example, 15 dB. Overall, what we observed is that we have a problem in the sense that we need to compensate for around 20 dB in order to have a viable subsea solution. So this is where things were, I would say 3 to 4 years ago. And what we tried since then is just to actively come up with a solution on how we can compensate all of those losses. And this is what we came up with. This is already 2 years old now, a little bit longer. And for those of you who want to know more about our solution, I encourage you to take a look at that paper here from the SB Norway conference. And what you can see here, I know this is a convoluted slide, is that we have our DES interrogator. And instead of going straight from our DES interrogator into our Christmas tree at the seafloor, what we introduce here is the use of sucker circulators. So what those circulators are, they're just glorified roundabouts pretty much. And what they allow us to do is introduce 2 fiber optic lines going from the DES interrogator located topside to the Christmas tree at the seafloor. And we're going to use those 2 fibers to have a kind of highway system where we're going to use one to send light down and one to send light up. By doing so, we don't have that collision we had before, where we had to wait for the light to go down all the way before we could send a new light pulse, because in here, we can have multiple light pulses going down and backscatter light coming up. So in other words, what this system allows us to do at the cost of having to add a second fiber is that at least the distance from the interrogator to the Christmas tree, we're going to be able to have multiple light pulses into our fiber. And it moves the constraint of only being able to have one light pulse in the fiber down to the actual downhole fiber itself, which, as we have seen before, is similarly, it has a similar length than in the tri-true world. So in other words, out of a sudden, we can achieve similar pulse repetition rates as before, just by the, adding a second fiber in between the DES interrogator topside and the tree. And then we also added a couple of other things. One of the things that we, as well as many of the other vendors, are moving towards in the subsea world is, instead of using standard telecom fibers, we're now using enhanced backscatter fibers. And by doing so, we can compensate for a lot of the losses that we're going to take in here. And then lastly, also by using this kind of 2 fiber system, we can also add amplification on the receive set, for example, and all of this would be located topside. And by doing so, for example, we can selectively amplify the light that is coming down from this part of the fiber, just because this is all that amplifier is seeing. We are partnering all of this with FMC. So this is the alliance we have with them. So in other words, we would supply the topside equipment. FMC would be in charge of supplying everything that goes on the seafloor, including that circulator, for example, which is a passive optical device the size of my little finger. And they package that in a 1 atmospheric canister that goes next to the Christmas tree. And then our scope would then again be to supply the enhanced backscatter fiber. Back in the day, and I'm going to skip that, or I'm going to talk really quickly, we'll have to modify, obviously, or to show that what we are doing really gives us the same data quality than our converter land system. And so what we did, we went out to the field and basically hooked up our quote-unquote land system, which is just a DES interrogator directly to a fiber that is installed downhole. And then we also used our Odyssey system that uses engineered fiber, that uses that remote circulator concept. And we tested different loss scenarios, and we tested different step-out lengths. And what we were able to show by using this way of looking at the SNR of the acquired data, where we just said, okay, for VSB, the signal corridor is just the first break. And then we just say that noise is everything that happens before the first break. And then we just take our SNR, that indeed with our system for a 12-kilometer step-out case with 6 dB added attenuation one way, we truly get similar data quality from our subsea system than we're going to get from our land system. And in fact, what you can see as well is that for shallower sections, our subsea system is even better than our land system. And then just as we go deeper, we start to catch up. And one of the reasons for that is that when we use enhanced fiber, since there is no free lunch, one of the penalties is that enhanced fiber has slightly higher attenuation. So not the 0.2 dB that I've shown before, but we're coming in at something that is closer to 0.5. And that's just something that catches up with us as we go deeper along the fiber. This is why you can see that those two are the same. And then the good news is that all of this doesn't come with the penalty of having more or less signal. You can see here that the signal, again, this is just the energy of the first break, is identical for the two, but just in terms of noise that is happening before the first break. And you can see here that the subsea system is just slightly less noisy than our land system. And then this is just what we did at the end. So we hooked up a 52-kilometer long fiber. This is very similar to what Andreas showed before as well. We didn't expect much because when we did this test, we didn't really optimize our system for such a long sensing fiber. but we're very pleased to actually see that even for 52 kilometers, we could still see a clear first break, even though that as we went deeper, you can see that we would suffer from some SNR issues, which at least showed us back then that we can probably push this out to 20 kilometers, but then as we go even longer than that, we need to make further modifications to our system. If you want to know more about that, there are two papers that I would recommend you guys to look into. There is one from Glenn Wilson, this is from the FCG, and then we also have one in the Leading Edge, where we talk ad nauseam about this data set and how we actually showed that our system is viable for subsea. So I know I only, basically it's already 10. So really quickly, what is going to happen next in the subsea world? So one of the issues that we have in subsea is that we cannot use Raman-based TTS systems anymore. The reason for that is that Raman is very photon hungry, much more than Rayleigh DES, for example. So one of the things that we're trying to actively pursue right now is instead of using Raman DTS, to go to Brilliant DTS. Now, one of the challenges of using Brilliant DTS is that similar to DES, it's not just sensitive to, in this case, temperature, but also strain. So one of the challenges is to actually, manufacture, I would say, a cable that is strain-free, and whenever there's any change, it's temperature. And then at the same time, on the algorithmic side, just have algorithms in place that allow us to back out any remnant strain from the temperature data. And we worked quite extensively on that. And actually right now, Brian Seabrook from ExxonMobil is presenting a paper on a field trial that we conducted last year at the SBWLA. So once that has become published, I strongly encourage you guys to check that out, because what we actually found, which was very encouraging, is that we actually are able to get DTS data from Brilliant, which has a much better optical budget that is very similar to what we get with Raman. So in other words, it looks like that we do have a DTS solution for subsea that is not Raman-based, just by moving from Raman to Brilliant. And this is just a couple of pictures where we show what we did here. So this is the setup where we had actually 12 wells that were hooked up to a DAS and a Brilliant DTS system. And then, which is not shown in that picture, we also had a different rack where we had a standard Raman DTS that was connected to a multi-mode fiber. And then we just took those measurements simultaneously, and then we compared those. And then the next step that we want to do is that right now, all subsea fiber installations are limited to a single fiber feed through in the tree. However, we're working with Teledyne to actually get a Christmas tree qualified that will allow us to install more than one fiber downhole. And once that's the case, then we can do much, much more in the subsea world, as for example is shown here, where we can have fast TTS and even, for example, fiber optic pressure temperature gauges all operating at its unique fiber. And then what we're going to try to do is we're going to try to do all of this without increasing our footprint at the seafloor, meaning that we are going to use the same transmission fibers for all of those three, and we're just going to use double DMs, which are wavelength division multiplexers, just to combine the light from those three, go for the same transmission fiber, and then at the seafloor next to the tree, we would actually then demultiplex that and then send each of those light pulses into their own respective fibers and get our own measurement from there. And then lastly, one of the things that there's also a strong push in the subsea world is just going to those longer reaches. So right now, everything that I've shown, we pretty much qualified our system to step out length, meaning again, fiber distance between top side and the tree of 20 kilometers. When we want to go beyond that, we need to come up with new systems of just amplifying the light. And one active field of research for us right now is just how can we do that? How can we get to those, say, 100 kilometer length? And one way to achieve that is if you use what is called distributed Raman amplification, where pretty much what you do, you just have a light source that you can hook up to each side of the transmission fiber that feeds light into the transmission fiber at a particular frequency. And that will then feed the light pulse that is emitted by DAS and TTS. And what we are trying to do here is basically get rid of the 0.2 dB attenuation that we're suffering. And with Raman, what you can see, for example, is that we can actually get much more light back. And this is showing here 40 kilometers. Or again, on top, without, and here with, and you can see that there's much less attenuation going on. So we're hopeful that by introducing that, we're going to be able to get to those longer distances. And that's going to be presented at this year's 2022 Image Conference. For those of you who want to know more, I just put a couple of publications here. These are the ones that I actively cite in this slide deck, but I hope that as you go through those, you're going to fall into the rabbit hole and you're going to see more of these publications. But I highly recommend you to check these out. And if you have any questions, please feel free to reach out. Here's an email address. I'm always happy to get some feedback, and we'll try to get back to you as fast as I can. With that, thank you very much. My apologies for running a little bit late, but I hope we still have a little bit of time for some questions.
Thanks, Andreas. So any questions? So for this, so right now for this subsea, that could be the wet tree things. Sounds like very popular in industry. So how is about right now it's 52 kilometers. So do you think we can go even longer?
There is certainly a push in industry to go for it. There are a couple of subsea fields that are coming online pretty quickly that are going to be beyond 50 kilometers. So for example, Equinor in the North Sea, they showed us some sketches where they show that they're going to have an FPSO. They're actually going to try to have tiebacks that are going to go all the way to 100 kilometers. So we're going to try to work on it, but it's going to be challenging for a couple of reasons. So I think that whereas I think as an industry, we are there in terms of having a subsea solution for step out length of say 20 kilometers, I still think that there is some research to be done to be able to go to those longer step outs that may potentially reach 100 kilometers.
Yeah, here another question. Why for the wavelengths?
Sorry, could you repeat that? Why?
Why 4 wavelengths?
Oh, why 4 wavelengths? Oh, that's a very good question. So let me try to go back. Yeah, maybe this one here shows it already. So in that, the backscattered light, as you can see here, is not the same as a function of distance. So it happens if you use one laser that sometimes you get a lot of light back for one location, but then it happens that as we move a couple of feet down the fiber, we get very little light back. So what can happen when we only use one laser is that for those locations where we get very little light back, we get into what we call fading. In other words, we get no light back, we try to extract an acoustic measurement from that, and at the end of the day, it's just noise. So one way to overcome that is just to increase the number of lasers that we use. Because it happens to be that fading phenomena is wavelength independent. In other words, if I use wavelength 1, I may get fading at location X, but for wavelength 2, I may not get fading at location X. So by using multiple lasers, we're then able to selectively choose which backscattered light from which laser we want to use. And by doing so, we get rid of the fading and increase overall data quality. And if we start off with 2, now we're moving to 4, as other vendors are doing as well. Maybe in the future, we're going to see systems that use even more wavelengths. The problem at one point is just the amount of data that is generated with each of those lasers, which is why there's right now, at least there's an upper limit as to how far we can go with the amount of lasers that we employ.
Yeah, there's another question. Could you explain a bit more about the Raman amplifications? Raman.
Yes, certainly. Right, so Raman amplification is actually a concept that is used in the telecom industry quite extensively for when we want to do, in my case, for example, make a phone call with my family in Europe, then we already have to traverse those extremely long fiber lengths, right? In order to boost those signals, what is used is Raman amplification. So in Raman amplification, you take advantage of the Raman effect, where you have a light source that operates at the Raman frequency, which is in the 1300, 1400 nanometer range, and you consecutively feed that light into the same sensing fibers. And then a physical phenomena happens where that light happening at those 1300, 1400 frequencies gets converted into the frequency that DAS is using, which is at the 1500, and feeds that light pulse. So in other words, as that light pulse is getting smaller as a consequence of just the natural attenuation happening in the waveguide, it takes light away from that Raman. And by doing so, as you can see here in this slide, we're able to delay and in many ways mitigate that attenuation. And whereas you can see here the 0.2 dB attenuation, in other words, we get less and less light back along the sensing fiber as we go deeper. With Raman, we can actually keep that the same. And only here at the end, we can start to see that we start to lose some light. So this is more or less how it works. One of the things that we always need to be careful when using these kind of amplification techniques is that out of a sudden we increase the amount of light that goes through the sensing fiber dramatically. And some of those components, and here's particularly the ones that are located in the tree, are sensitive to those high optical energies. So what we would need to do is just to make sure that not too much light enters, for example, the tree in order not to damage any connectors that are in there. So something that I'm not showing here, but something that we would use is that at one point here, we would probably have a type of WDM that tries to dissipate the Raman light before and prevent it from entering the downhole fiber. Again, just to prevent any damages to any of the optical connectors that are in here. And I can provide more information in terms of papers that talk a little bit more about how distributed Raman amplification works.
Okay, thank you, Andreas. So I think we're a little bit over. So let me just hand over to the Casey to close this out.
Thank you, Yingping, for moderating, and to Andreas and Andreas for their presentations today. The recording will be made available on the IRIS Earthquake Science webinar playlist. If you are interested in future DAS webinars, please join the DAS mailing list and check out the DAS RCN website. Thanks so much for joining us today.